Hello. Uh, Hi. Hello. Thank you very much for logging on to our text section today. Many of our associates, the scientists, members of text who participate, especially Christopher O'Neill, is not able to be here today, but I just want to give a brief updates um, on what's going on. One of the aspects is, of course, the tech next week won't be here because I had to be away. And so we will resume again on the 16th of November. And after that, the 23rd of November, I will have the episode 8 of the history of physics that's we are being successfully going on. And there are a lot of viewership. We are not yet advertised in the public arena, but I think we plan to do that. The episode 8 may be one of the crux aspect because it covers the real history, but then it moves into the current emergent theories uh, of how to bring together the quantum physics and general relativity, which has always been a big problem. And the present understanding that I also will adopt is about the M theory, which advances from the superstring theories, the five superstring theory, kind of unifies them into one arena. But when it does that, it talks about brains rather than super strings. So that's a very important aspect. I do find that the brains may give answer uh, to the idea of discontinuum physics that I am doing with Emery Taylor. That seems to have very fundamental basis, and we did some program uh, simulation that shows that in the electric and magnetic fields, the fine structure constant automatically comes into picture in terms of the phase difference of the sinusoidal waves. So it's a very exciting thing that we'll be publishing soon, and that may hold the key how the brains may be separated by the discontinuum length. But within the brain itself, it depends on the condition. Original Hermann-Pullis formalism talks about a harmonic composition of the fields. And that brings the idea of zero point field, which is like cosmic micro. I mean, eventually we can measure as a cosmic microwave background. So that connection is brought out in one of in the recent peer-reviewed papers, and also a few of them are coming up. So when you tie up all that with mathematics, you see that we probably what can measure the zero point field in terms of the cosmic microwave background. Of course, we know about zeta wave waves, which we believe may originate from the superluminary noisy general condensate that is the essence of the one of the essence of the higher molecular formalism. The other aspect is the formation of micro black holes. Um, so locally, because of the distorted fields, and the distorted fields can come about uh, primarily we think there are monopoles in the noisy condensate, and these monopoles are separated, and they can travel at much faster, close to infinity. I mean, they can zip through much faster than the speed of light for sure, and but they come together, the north and south poles, so to say, comes together, and you know, they form a horde type of mechanism that John Hodge has talked about, and he's in his scalar theory of everything. And we have published together all of the group, most of the group has published together paper in Canadian Journal of Pure and Applied Physics, Sciences, or we call it CJPAS, a few years ago, a couple of years ago. And in that one, we describe the understanding of how the the hordes, which are the dipoles. I believe that is believe we right now the conjecture is that uh, monopoles, they come together at some point uh, because of the natural churning or chaotic uh, superluminal dynamics uh, of the condensate. Uh, so in that, it's you can imagine a mesoscopic like a sea, a huge sea like Atlantic Ocean, Atlantic Ocean especially, and the churning action somehow creates vortices, and these vortices are the key points where you have the formation of these hordes, as well as from the hordes, because of the distorted field, the high energy aspect will create particles, or partons, especially. Uh, and these partons, uh, we believe, or unparticles, create a hot PDP mechanism. And in the original PDP mechanism, which is also called as the Pauli-Dirac Planck acronym for that PDP mechanism, that published together with Christopher and Manuel Malauer, that's a physicist. And we also have a separate paper with Emery. I also have a separate paper with Emery and Manuel. So we have different combinations of us publishing together, and separately in astrophysics and with Manuel Malauer, as well as separately with the Emery Taylor in discriminating physics. And then all of us also come together, especially in the experimental aspects, to Christopher. And earlier, the manual, we have this paper that talks about how you can use a 2 by 2 matrix to from the Helmholtz decomposition to describe the 0 point field and the microparticle aspect. Microparticle comes because of the vortex nature. So you have the transverse waves, they are like open strings, so they are not visible, whereas the vortex aspects creates a closed loop, per string theory, and that creates a distorted local field. That creates all these mechanisms, and we believe that microparticle, the gravity aspects come in that aspect. So you have the, it should create a gravitational waves, in other words. But these are microparticles, very micro gravitational waves, so to say. And depending on the signal to noise ratio, they may not be measurable in that sense, a normal sense. But I think the effects, when you accumulate, the microparticles can accrete, and many other recent studies in physics had pointed out possibility that even Sabine Hasselfeld said that there could be a microparticle that could be slipping through your brain, a very small black hole. So they could be there everywhere, and we should expect that to be everywhere, right? Like dark matter or dark energy, because that's the essence of the whole universe we are talking about. So they are created all the time, and it was an ongoing process. And in that one, because journey effect locally, they create these vortices, and that is the point of where the origin occurs. So I just briefly want to uh, show you one of my most recent publication, a chapter in a book, and in that one that I'm going to share right now. I talk about okay. So I talk about yes. So this is what it is. One of chapter. Let me zoom in so you can see it a little better. So this is I'm going to put it in ResearchGate as well, because I just want to. Pretty soon I will be putting in the ResearchGate this one. Just want to ensure that all these are taken care of. So here I have the chapter uh, in the futuristic trends in physical sciences. So IIP series book that has been published recently. It last year onwards we have been year more we have been doing this, and then finally they are able to publish, and I should be able to get a hard copy soon for this. So so in that one I have published the quantum physics general formalism theoretical to experimental gauging. And in that one, I kind of summarize, give like a review, summary of what was going on till about last year. And we talk about the hot PDP, the higher markerless formalism, the hot PDP mechanism. So let me go into some aspects. I just want to show you highlights of that, but you may have to go once I put in RG, it will be easier to check this out. So talk about go back and like history of physics, I kind of go through a little bit of how Galileo, Newton, and all did that, and how that classical physics led to quantum physics, and very very small aspect, and then talk about the Maxwell equation, which forms the basis of how the electric magnetic fields come together. Uh, it's something very fundamental to all the physics, and that how the Kirchhoff's equation come to the picture, how the black body radiation, everything. Uh, Eventually, I had to come up with solving the ultraviolet catastrophe. So solving that, Planck had to come up with the idea of quanta of energy. And then later, of course, we know vacuum catastrophe, which uh, the problem between quantum mechanics and the relativistic theories, uh, you know, uh, is something that is ongoing, and we have to still resolve that. But the idea of black holes, short-styled matrix, things like that, and how that led to the idea of how initially there was a problem of information paradox, things like that. But the Hawking's radiation said that no, the black holes are you can measure black holes in some ways, presence of black holes, and right now all the telescopes are towards that, and then have been able to resolve this criteria and able to sort of able to uh, get the image of the black hole through the telescopic methods, special telescopic methods. But what I want to point out is the to unify, we have to understand also the strong aspects. So you have the quarks and leptons. Quarks have the color charge, and we know that's a mediation, Feynman diagram, things like that. But the idea of weak nuclear force has been proved, and that forms the basis of the standard model, as we know, the W and Z bosons. But then the Higgs field is the one that is filling the whole of space. So this has been proved, and then the Penrose came up with the Nobel laureate. These are Nobel laureates as well, as I have pointed out, Higgs and Penrose and all. They have come. Penrose came up understanding of conformal cyclic theory. The universe undergoes infinite cycles of expansion, contraction. The Parisi's proved about the spin glass, again a Nobel laureate, recent one. Magnetic atoms. So he proved with the mesoscopic level to understand how to bring to the neural networks uh, and how they can change over time, things like that. So I am talking about conservation of time. That's the real ongoing research with me, and I'm publishing that. It's ongoing process right now. So the highlights, I bring out the highlights of the higher marvelous mechanism. How is that advanced to this the whole people? It remains higher. Markulik is Malawer, O'Neill, Hodge, Zhang, and then Taylor. were our associates. This is an acronym for that. So hot PDP mechanics that I said, the CJ or Canadian Journal of Pure and Applied Sciences. So this is the stuff, and the 2x2 matrix. And I briefly mentioned about how the 2x2 matrix come to, and then I come up with the statement of the problem, how we came up with the understanding how to come up with the 2x2 matrix. And then we solve it, and we came up with a very simple formalism of from the decomposition. So this is our actually this is the gradient, which is of the field, essentially the 0-point field, and the rotational aspects or the vortex aspect is the macro backbone. So it's a very simple. So we solve normal matrix equations like Hamiltonian, like Schrodinger equation, is similar. So we get eigenvalues, and then when you plot that, we get generator pulse that shows that we could have faster than speed of light is possible. So wave function collapse and the macro backbone using a fundamental understanding inner product, outer product, and I have fundamental mathematical formulation which connects from the simple understanding of the matrix operators to the final understanding of the wave function forms. With Malio-Malaver, there's a very fundamental mathematical derivation, almost like a pure mathematical derivation. So that's a very fundamental. And from there, we came up expand this higher modulus matrix, and then we get this superstring, the string matrix, what I call a string matrix. So we can expand that, and then later on in the present foundation, I say that because the clocks. So I'm considering about the clocks, time conservation, and the clocks. This will keep expanding, and this will start contracting because the macro backwards, they have a habit because they're inner spiraling, they contract, so they can produce brains. That's what I'm saying. So that's the important aspect that's going to develop, and I'm going to publish. It's in the publication process, these aspects. So the signal-to-noise ratio, very important aspect, not for it. That's the problem. So can we measure it? It's a whole question. Can we observe it? Can you measure it? It depends on the signal-to-noise ratio, right? If it's very noisy, we cannot. So, but there are some constitutive equations that connects the signal-to-noise ratio. How, this is a very fundamental equation that can be used to figure out the signal-to-noise ratio. And based on that, I came up with this understanding of how to measure that in terms of signal-to-noise ratio. So this is a very important aspect for experimental observations and measurement. And we could develop experiment, experimental design, instrumentation to measure that. So this is a detail, some details of mathematics. Again, this is just I have papers that gives more details about that, which I have given the references. So based on that, I said that there is a critical signal-to-noise ratio, and below that, the phase, the phases separate, and also then we cannot measure. We cannot, the instrument cannot measure that. So the instruments need a critical signal-to-noise ratio in order to really sense or measure that. And this is the fundamental aspect of the PDP mechanism, where you have the south pole, the monopoles, and the positron-electron combination. But eventually, the later papers, I have few papers that bring out the fact that it could be on particle or part, because they may not, the positron electrons may be forming a little later than that. So the primary aspect could be partons or on particles. So based on this analysis of this PDP mechanism, you can come up with the understanding of how these fields then become like supersymmetry or SUSY, called. So that's a very important description. But John Hodges has published that actually the south poles are a little stronger than north poles, and then so we have a deviation from that. So that becomes an anisotropic eccentric position. We move on to understanding scenarios. So many scenarios we came up with and published along with Christopher and and then another paper with Emery. And we mentioned how the dipole mechanism come into being. Like I said, north poles are coming to the monopoles are coming together from dipoles, but how they are coming together and then creates what kind of a morphology. So you have morphism, things like that. Eventually, we'll be talking about that in terms of space aspect, especially how they come together. And this is a scenario we are like 10 scenarios almost. And then this is a scenario we think that's the most probable one. So how the electron positron come together and how the north and south pole come together and create a compression space-time. And that's very important because compression-based time may be the whole key to understanding not only gravity, but also how they create additional things, distortion, vortex, that eventually could produce a false vacuum, things like that. And that may be a crucible for strong nuclear formations, quarks and things like that. But the pointing vector is another aspect. So you have a pointing vector based on this. You have the electric field and the magnetic field because of this. So you have a pointing vector, electric field times the magnetic field, divided by the mu naught, which is the permittivity of space. So you have permittivity and permeability of space also coming into picture, and that's how the speed of light comes into picture. So we know that the vacuum is created from these mechanisms that holds the speed of light constant, and you have the permeability and permittivity coming into picture there of free space or vacuum. And that is the one that delineates and help to create eventually, and the particles then pop out through the vacuum, and that creates the subluminar, what really our living world or the real universe. So these are the larger understanding of the physics that's going on, and we came up with estimates of the sizes of the monopoles and fermions, so is how they all fit together, and also space-time. So we can measure that, and I did the calculation, and it corresponds to the one that is done with the astrophysics as well as some of the quantum physics, the LHC, the astrophysics with some of the telescopes. Of course, the new telescopes, James Webb and other telescopes are really coming up with very new observations that could change the paradigm of physics itself. That's ongoing, exciting things. That's good. But based on that, I bring out the understanding of how the discontinuity could come out, and the gauge aspects come into picture there. The gauge transforms, things like that, for the discontinuity physics, discontinuous energy fields, things like that. So that's a very important formulation. All these formulations are then used together to figure out the mathematics of what's going on. Then I solved that for a mesoscopic level using how very simple experiment of ducks and swans swimming in a lake, and I analyzed using this fundamental quantum equation, and I could actually find out a way to measure them, and we can actually verify mesoscopically some of the relationships. So that's an interesting aspect there. The other aspect is the density matrix. As we know, it's a very important formulation. So that's what it helps us to understand how it is spreading the density, which is the key to understanding spread of mass and then gravity, things like that. So micro macro space. So that is the other formulation. So all for fundamental abstract math can come to the real universe math, which can be verified using mesoscopic, certain clever critical mesoscopic experimentation. With the, but do we need advanced tools, and we can even create a laptop experimental methods to verify to prove these aspects. So quantization is connected with the radar signals as well, and I bring out in one of the papers that I have talked that the telemetry which is used in space exploration, the gravitational aspects, how they come into being because of the vortex nature of the gravitational. So there is a connection between magnetic, electric, elastic, gravitation, torsion fields that Alexei Sekarenko has pointed out, and how the coupling occurs. They have found out all the coupling constants for these. So that's a very important aspect. Again, you can use Feynman, and I applied Feynman diagram to find the quanta, how they spread out the monopoles, how they come up together. Sorry for the figures, but you have to look at the original figures. This didn't come out well in this book, but if you refer to the original book, the original reference, you get what exactly is going on here. So it didn't come out with, sorry about that. But you can use that. Hi, Christopher. Are you there? Oh, okay.
Yes. Hi.
Yeah, I'm just, I thought I didn't see you, so I just going over the present. I don't know whether you had a chance to see it.
Yeah, I saw some of that. Yeah, it's
Yeah.
daylight savings time kind of screwed up my.
Oh.
Yeah, it's the hour moved forward. I forgot. We're back.
Oh, okay. Because the 8:45, I don't know. I keep the same time. I like we discussed last week. I'll keep the same time, 8:45, to be standardized. Yep. You may have to adjust according to that.
That's it.
Sorry for that, but yeah. So I said it's 8:45, and then so the standard the UTC has changed. I didn't. So I should correct then.
Or rather, no, I don't think the UTC changes. The other one changes.
Oh, you are okay. So UTC is still the same.
Yeah, that's right.
Okay, so that's what I want to keep UTC. So you have to refer to the UTC to adjust your time.
That's correct. Yeah. No, I just forgot.
Everything is okay. So we can proceed the same way, but then whoever comes in, you have to adjust according to the UTC.
Yeah. Okay. So that's fine. So you're going over a paper?
Yeah. So I just should I just finish it and then we can start?
Yeah, do. Yeah, finish it.
Yeah. So I'll continue. What I was talking about is is my chapter in the futuristic thing that I'm going to put it in the RG pretty soon. I just looking to see the proper timing for that, but I should be doing in a week, end of this week or by next week. I will put in the RG. But I just want to go through the main aspects here, and I have many references. But how I came up with the understanding, from the IMR list and how we did that, that I talked about our understanding of the PDP mechanism, and then we came up with how the reconfiguration of the magnetic and electric fields, and that eventually proved about the SUSI. So I kind of, it's like a summary. So it's the SUSI aspect, but the John Hodges thing says that, okay, South Ports has to be more. So there's asymmetry brought about by that. And I talked about how the brain structure could be understandable from the understanding of the string matrix that I have expanded from IMQ. So you see that here, I'm talking about the clock speed. So the current physics paper that I'm doing, this is almost a Galilei proof. We are getting towards the Galilei proof now, but I had to do some revision. So in that one, I talked about the clock speed. So along the 0-point field, the clocks will run faster, as we know it's relativistic. So this will stretch. Whereas along the micro backward direction, it will contract because of the the clocks will run slower in the higher gravity in the micro backward. So it will compress. So you get a stretching and then compressing. That becomes eventually like a thin film or a membrane, which is the basis for the membrane theory. And then I talked about how the brains may be separated by this continuum length. I think earlier I talked about briefly about with Emery Taylor's discontinuum physics. So then we have a way to understand the brains. And the brains themselves, now I have two things, the 0-point field as well as the micro backwall. And the micro backwall is a local distorted field. Again, I bring about how that distorted field comes about, the vorticism in the chaotic superluminal condensate. And this is an earlier one last year, and after that I have many papers that came out, a few papers. But this one, what I was talking about is just a gist of that algorithm, how I came up with the understanding of general transforms. So I give you briefly that how Laplacian and all the Fourier and everything comes together. And finally, we can plot, we can understand the gauge field versus the time. Everything is transformed to time. The time aspect, which can has this complex transformative function. And then we can use that to do experiments. And I briefly talked earlier also how a signal to noise ratio comes into being. And this is the light direction and the magnetic direction. And we can measure it using an oscilloscope and some processors, microprocessors. So finally we see about the bundle, how we can convert inverse transform and get the time out of this, out of the general transforms. So the time aspect, this is the main thing that I have given in the ICFAS conferences about the local time and global time and real time and proper time, how the 2x2 matrix, which is a vectorial tensor aspects of the time. The tensor aspects come from here, in a sense, the concept of the tensor, and then expanded to the rank 6 tensor of time, eventually. So this is before that, before the rank 6 tensor is the one before that. So it's a continuous derivation. So then I can describe the discrete energy field, which is a distorted, which is what's creating eventually the distorted fields. It's connected to the gravity aspects. So we can bring out the gravity aspects in there. These are all abstract derivations. So, but somehow we are able to bring it to the real world, and that's a big thing. And then we talked about how we can do a switching circuit based on this. And we did some connection between different modes of the switches itself, fundamental aspect. And then based on that, you can come up with a waveform. You see that different waveforms. So you get a modulation. So the idea again goes back to understanding of how the superluminal noisy thing become a signal thing. So among these signals, which is noise, you can create which is noise, which has a very low signal to noise ratio. You can create signals of this nature because the particular way that on and off works switches. It's a fundamental way. Some of the, I said I apologize that some of them are kind of meshed up here, but we have to look at the original thing. When we put it in there, it kind of meshed up some of the equations or even graphs. But so we can now come up with the global and the local metrics for these. So again, although it's a little bit of heavy math, but these are derivable math. Unlike what is there in the actual literature, it's very hard. Even quantum loop gravity, things like that, gets into deeper aspects that the string theory especially has this problem. But I think these are all we can even reset to eventually to very simple algebra. So that's a good thing about this. And then we talk about that, and we did a lot of analysis based on that, and we got this understanding how the superluminous magnetic plenum behaves, and we get a mapping. The fundamental thing is interesting thing is that these are all derived from the abstract things, but they connect with the real universe in some ways. So we get this crystal kind of outstanding, and that could point out about the hot PDP mechanism, how they come into being because of permutation aspects and the prime number factorization, things like that. That's what we are going at. And you did that, all this computer programming. Then the state of the clocks, this is the idea. So I am not connected yet, but this one is a very important thing. And that also connects to the state of the clocks, and what I'm bringing about the tensor aspect, about how the clocks behave faster, in a particle that goes at reduced speed. So inside a particle, the clocks can go very fast. Outside the particle, because of gravity, they can slow down. And how that creates a lot of anomalies and all the things that we see. So again, this is the switching states, depending on how they go, how the off and on connects with the on mechanism. You get a fluctuation or you get a flickering. So these are the things you can see. So you get a quantum global, how the chaotic waveforms in a superluminal thing could be occurring. So we can reconstruct these mathematically, and then we see that that's how the noise is. So based on these modes of the switches, which are binary, of course, become ternary because we have a zero mode also, like a quantum computer. It's the opposite of quantum computing, just talks about on and off, and also superposition of on and off. But I'm saying there is a fourth one, which is just zero mode. So you have a zero mode where it's neither on and off. So these are the key things here. So that we can evolve the geometry of space that eventually I'm going to work with Christopher once I finish all the temporal or time aspects. So here again, this is a little better picture of how the monopolar use the Feynman extended Feynman diagram to see how the North Pole and the South Pole, these are the fundamental things that's well within the superluminal thing, right? And so this is it's mediated by the superluminal magnetic plenum, that plenum that John talks about, and that can create a hot mechanism, dipolar mechanism. So this is monopolar here, but they come together and form a horde, which is a dipolar. And this dipolar eventually creates this PDP, that PDP mechanism, we say horde PDP mechanism. And then we have this horde PDP, which is just electron, positron. Now, they could be partons, they could not, or ion particles. They are not stable particles in that sense, the normal sense. But then we have a photon wave there because of the electron. As we said in the original schematics, the electrons, the electric field and magnetic field come together. The schematic diagram of the 10, we see how the horde PDP, electric magnetic fields, come together, and they create a compressed space-time wave. And that creates eventually a photon wave. And this photon wave eventually creates, okay, I have to look into more quark and quantum. Of course, this photon wave, what I'm talking about is the color charge, all these come into picture there. So we need expand this aspect, what these are. So that's the other aspect to consider. So in order to make it correct, we need much more theory understanding of how this comes about. In any case, these are just conjectures now. So based on this, we can talk about a dimensional range, how this dimensional range can come into be briefly. So if you have 0 to 1 superlunar planum, they are not observable because they are like open strings. We need more than that. We need like a line, 1 to 2 dimensions, which is like line to plane type of thing. The open strings, 1D closed strings, so they can form closed strings, and these are partially observable. Dimension 2 is a horde that will have no thickness. That John also emphasizes. There is no thickness for the horde. Again, they are transparent, and because they are not observable. So even if we try, probably even with the best instruments, we may not be able to see that. So we need a dimension 2 to 3 particles like fermion bosons to be observable with like LHC or some optic method, some electromagnetic techniques. We need dimension 2, 3 to make it observable. So these things are not observable. Then we believe that the dimensional range 3 is the matter universe that we live in, Euclidean, observable. And there are things like fractal dimensions, things like that, that talks about how you go between 2 and 3, and their fractal dimension 3 to 4, things like that. So 3 to 4 will be space-time manifold. Black holes, they have observable effects that we are able to do with the specific types of telescopes, are able to observe the effects that's created, even horizon, things like that, of the black holes. Then 4 to 5 is where the horde PDP assembly dynamics affects quantum physical. There again, 4 to 5 again may not be observed. So if you only in this range, some observation is possible. These are outside of that observable ranges. So that's very theoretical. From the abstract lenses, we can design the experiment, what the experiment can possibly do, what it cannot do. We can come up with an understanding, and this table will be helpful, I think, eventually, to figure out that you cannot keep trying out. We are not going to see it. We have to be in this dimensional range to observe that. So that's a very important conjecture table, important aspect for experimental physics. So how the time and space and sense and ever connects, this kind of gives a sketching of how the time event connects to sense and time. And this is the initial aspect. Later on, I'm going to develop a little more on this aspect. These are all initial conjectures. So how the linking occurs, so you can put some mathematics in the Feynman diagram, and then in terms of the wave function and also the phase angle, phase difference. So how that connects with the Feynman diagram is what this is. Again, I need more. But another aspect is strong gravity and weak gravity. I believe that eventually that may be the key, because the weak gravity that holds the in the open strings versus a strong gravity. And then, as we know, in the brane theory, they come together, all the strings, and they become branes. But how that gravitational mass come in there. I think I have a way from the tensor time theory. I connect with the gravitation gradient and then see how they interact and creates. So I expand more on the strong and weak gravity aspect there. The equivalency principle you can apply, and that's the other aspect. Some mathematics I am developing. The equivalence of the weak gravity of the acceleration versus the gravity. But in this case, the equivalence between weak gravity and strong gravity also can be brought about. And how the weak gravity and the strong gravity works together, chain reaction, is what this is showing me. So the masses are spreading out. They have density matrix that gives out, and how they become attractive. The idea is that how did gravity essentially attractive? Why is it? So essentially they are pushing each other out, right? The masses. But when they come together here, this pushing out, although they are pushing out, they eventually creates a virtual attraction. They come together because this one pushes here this way, this one pushes this way, and so they kind of squish each other, compress, and this compression is where the gravitation effect comes into picture. Very similar to the distortion. So these are all happening happily in the superluminal thing, but when they come together, they squish together. This is where the distorted field is occurring, and the strong gravity aspect comes into picture. Very simple way of looking at it. Essentially, there any particles coming to each other, or even partons, anything that any entity has the habit of occupying space, and that we know under other than the photons, they don't intermix to each other. They are mutually exclusive in space. So especially fermions, they occupy a space and they don't allow any other things to come together, and they push them out. So that's the idea here. So the weak gravity is like open strings there pulling, and the strong gravity is like a rope, which are gathering of different strands together, and so they have larger force. Okay, so if you have a very simple thread, for example, it can probably pull a little, small ball or something, but anything larger than that, it'll snap. Whereas we put threads together and form like a rope, they intertwine them. They can pull very large objects, right? So that's the idea of strong gravity. So like a rope. This one is like a thread or string or thread. So weak gravity is like a simple string or a thread. Strong gravity is like a rope, which is in the correlation of the strings putting together form a large force. Okay, so that is the other aspect. The question of the true Watts vacuum also I bring out. Again, I'm going to work on that. The conjecture, I think, is kind of interesting. Okay, I talk about how the baryons, gravitons, gluons can be synthesized. So you have the false vacuum, higher potential energy than the true vacuum, and the false vacuum, it can form because of higher potential. It can create, like crucible, create enough energy, high energies to produce quarks, gluons. Now, I have not done the calculation, but that's something that to be done, or simulation. But in the true vacuum, which is much lower potential, much lower energy, they have leptons or baryons, basically fermion type thing. And here you have quarks like thing. And you could have a micro wormhole or something that creates the mediating as the gauge bosons that helps to create. So the gauge bosons are important to form the strong gravity. So they create in this quark mirror, they create that, and then finally the outside they are connected by the mesons and the gravitons. Again, gravitons are theoretical particles, not just been observed yet, but so you have the whole what you call like a bridge mechanism, connecting mechanism or circuit. So the flow can occur. The gauge bosons or leptons. So this creates a perpetual kind of thing that creates, creates with gluons, mesons, gravitons. So they create the low energy things as well as strong energy things, and in that the interplay of the weak and strong gravity come to picture, and they all come together. How they come. So that's the sense of the thing. I think that's mainly. And then I have the literature, extensive literature. I think I put all this stuff. So essentially, that that gives a bird's eye view or overall picture of what was going on till last year. Essentially here. So most of the important, key. There are a few more, of course, papers that we have done, but these are and other things in the literature. So I think that's kind of put together that. So they have published the book. I should be able. I'm sorry. I should be able to get. I should be able to get the hard copy soon. But I'm going to put this one. This is online copy, so I can put it in our RG. And that's the main thing. So that's one of the things I want to present. Christopher, you are there, right?
Yep.
Oh, okay. So yeah, I don't see your pictures of that. So yeah, do you have any comments or something that you want to?
No. Excuse me. No, not really on the on that research. I think I've seen a lot of that before. I would have commented on it previously.
Yeah.
So I've nothing really to add to that.
Okay. Yeah, these are all things. I mean, just putting together things. So yeah, we are gone through extensive discussions of these, and but right now I think what we did last week, you were quite interesting. I think people are now there are more viewership. Even in our circle, more people are looking into that, and your thing has already reached high level. I mean, I just standard like 100 views are that Andreas and Emmanuel's Superhuman, they are like a standard, a higher level. I think we are reaching there. Your numerical relativity and things like last week. And, so these are because people want to see what is the next aspect, right? So I think the history of physics helped to eliminate. So that's the important thing. Eliminate all the previous things. So very carefully, algorithmically, step by step goes, and then said why those are not possible, why you have to move forward. But we don't throw the baby throw the baby out of the bath, but kind of do something better than baby, so that the baby can be happy. The funny thing thought occurred to me. Okay, the baby is happy, but is the bath happy? Is it important for us? Bath may be happy in chaotic situation. I don't know. But is there like a state like that? That's interesting to think about. But in any case, we worry about our human aspect, how we see the consciousness. So from that point of view, we have to do something that matches our environment. We should adapt our environment or design our environment so we can be comfortable and happy. So that's the essence of human presence there. Larger sphere, of course, things are different. I was thinking even recently a path of destruction or the axis of evil that you talked about. It's an interesting concept.
I don't remember talking about this.
Yeah, you talked earlier about the axis of evil in one of the.
Oh, that's such a terrible name, actually.
Yeah.
They shouldn't call it that. That needs to be renamed. So that's to do with the alignment between the CMB and the equatorial plane, is it?
Yeah.
Yeah. So that's a terrible name. They need to.
Yeah, that's terrible. But I don't know why it called that. But what I'm saying is that there's something like that.
It's called that because basically it seems to suggest that the Earth is at the center of the universe. So they need to change it to, I don't know, anything else.
Oh yeah, yeah. I mean, so that's what
we just called it the CMB Earth alignment.
Oh, okay. So CMB axis, geodesic CMB axis. Or
yeah, geocentric CMB axis. That's basically what it is.
Yeah. So that may be a better description. And thank you for clarifying that. So
yeah, it's just because they're always going on about axis of evil and political stuff globally. So
it's because of the we have religious connotations in terms of the God and the devil aspect and all that, evil and.
Yeah, well, I think it's more to do with the political side of things.
Yeah, political side. Yeah.
Whenever there's we won't get into it. So, but I think it's. I mean, I don't think it has anything to do with religion, really. Well, I mean, obviously it does, but not straight up. I mean, evil and good doesn't necessarily have to be a moral thing.
Yeah, actually, even in quantum mechanics, the quantum aspect, there's something called evil twin. I think we talked briefly earlier.
Yeah, we never really got into what that was, though.
It's the conjugate symmetry of the twin aspect that comes in the quantum, when you consider quantum mechanics, the many worlds and all. So you have the mirror aspect and the other aspect, the twin aspect. I think I don't know whether the what you call the chirality comes into picture, but the idea is that for symmetry, in terms of symmetry, there should be something opposite to what is real, right? So that is the evil twin. The good aspect will have an opposite aspect.
I don't know. You'd have to show me that. You'd have to show me that.
Yeah, there was. I had a YouTube, and people are very much in the 60s. During that time, the quantum mechanics were interpreting a lot on that. I saw a video. I had to pull up that. I forgot. There was a person who described very well how the mathematics also of the evil twin, why it should be there and things like that, or something that we had to consider. But see, what we want to do is distill these things, and then take out all these connotations and try to put it on, like you said, on a better perspective, for example, CMBR. That's what I'm trying to do. The two things we can measure are the CMBR and the gravitational wave, right? The GW, I call the GWs and the CMBRs. These are the fundamental measurements of the universe that we get here, the signals that we get here.
What's the DMW? Is that dark matter waves or something?
Yeah. So the GW gravitational wave is about the vibration.
GW, sorry, I thought you said DMW.
No, GW, gravitational.
GW, Right. Yeah, I get you. So they're called the gravitational waves.
Yeah.
Yeah. Background.
Yeah.
Okay.
So they create, in general, they're due to the matter or the masses, forming like black holes that creates the gravitational waves. So they are the vibrational aspect of the matter. Whereas the other aspect is the CM barrier, mostly due to the light or formation of the waves in some ways. So if we distill down the wave and matter, then try to see. So the wave aspect, the CMBR may be bringing out the wave aspect, whereas the gravitation may be bringing about the matter aspects of the universe in a larger sphere, in terms of the classical picture. So the matter and the wave, those are things. And then quantum mechanics says, yeah, both are interrelated, things like that, of course. And then Einstein says we have to see them in a different light of how that bending of the space-time itself creates all this, where the matter creates gravity. So the gravity becomes the main thing in the mix, right? So we're trying to understand that. So basically, then wave, what we measure versus what the theory says is the main thing. We have to distill it down.
Yeah. Well, I think I came up with something there recently. So.
Oh,
just earlier.
You want something to present now?
Like we've been talking about the 120 cell, and then we need to. That's a four-dimensional kind of hemi-geometric figure, and so it's kind of not the same as the hypercube, where you have this kind of cube inside a cube scenario.
Okay.
It's a little like that, but it's a bit different. So it'll be more. It's hard to describe, but more like the way the quasi crystals are, where, or if you have a grid of squares, then okay, that's a grid of squares, and then if you were to turn that into a cube, you would and look down one of the sort of branches or rows of squares or cubes, you would see one square and then another square inside that and another one inside that, and so just because of the perspective on the situation. And that's the similar scenario then with the hypercube, where a smaller cube inside a bigger one. It's not actually inside it, it's just further away. So that's well known. But let's say you had a square, and then around it you have just four squares, but they're distorted obviously so that they meet up. So that'll be I think that's called a hemicube or something like that. And so similar then with the 120 cell, it's a dodecahedron surrounded by 12 more dodecahedrons on all sides, and they're distorted just like the hemi thing is. So yeah, I don't know. I mean, I suppose you could say that is one dodecahedron inside 12 others. So that is one smaller version, and then those 12 others presumably create a convex hull of a what would you say, a 13th or 14th dodecahedron. So maybe you could say there's a smaller dodecahedron inside the bigger one. But either way, so let's say we're taking that now from the fourth dimension to a hyperbolic dimension, which is also four-dimensional, but we're going to have one of time. So what we do is, just like with the cube or the hypercube, where you kind of do have a hemi sort of cube thing going on because of the distortion. Looks like the other cubes around it are kind of distorted. So just like with the hemicube, where you have these four distorted cubes around the central cube, you could expand the vertices of the corners to, so each vertices actually will contain 3 vertices. And when you expand it out, they become cubes. So then you're back to your 3x3 grid. Yes. So you could do that with the 4-dimensional hypercube. Then each vertex on the corners would contain, I don't know, 7 vertices, something like that, and then they expand out to form cubes. So your hypercube then goes from basically a 3D projection of a 4D cube to a 3D projection of a cube, of a hypercube or 4-dimensional grid, essentially. So that will have that will look like a 3x3x3, because we're now moving into higher dimensions. It will look like a 3x3x3 cube grid. Excuse me, cube grid, but it's actually not. So it will be projected from 4-dimensional space. So as you rotate that in 4D, you're going to see a lot of extreme distortions on the sizes of the cubes and their arrangements and such. But we will never see that, so because it's locked into our frame of reference. So we're rotating. If the cube rotates, we rotate with the cube. So there's an invariance. So we never see this distortion. Although you might see it in certain cases, but you know, those would be put down to hallucinations, madness, dream, you know, alkaloid intoxication, these kind of things. So anyway, so what's the point I'm trying to make here is anyway, so this hyperbolic grid system has vertices on all the corners, obviously, of each cube, then also on the edges, midway between each vertex. So that gives you the 12, or no, sorry, isn't it? Is it 20 vertices in the dodecahedron? Yeah, that's correct. Because you'd have 12 plus the 8 on the corners gives you 20, and then so in order to this grid structure, which is the if you were to extend it to infinity, it becomes the fundamental domain of the Borromean rings. I think I'm saying that correctly. So so that's not too important. So basically, we can transform that into the Borromean rings, and that's fine. But we don't want to do that. We want to go and expand it in a different hyperbolic sense. So we already have 4. You know how, like, if you have a cube and then you can put another 4 cubes around one of the vertices in the cube. So because it's 90 degrees, right? So 360. But if we are in hyperbolic space, we can expand that, and we could have, well, any number. We can go up to infinite degrees around a single vertex. So we can do that pretty easily by shifting the mid vertex points on the edges and just moving them up, so that we go back to the dodecahedron. But now we have 4 dodecahedrons around a single vertex or edge, and obviously that's going to give more than 360 degrees of rotation around the vertex. So that's not really a problem, but basically we seem to be going from like a lattice structure that's 4x4 or 4-fold to one that's 5-fold, because it becomes we get pentagons on the faces of our cubes. They become pentagons to create the dodecahedron. So that seems to kind of, okay. So another way to do that transformation, it's pretty difficult to do on visually as well, with graphics, computer graphics. I'm working on it, but it's going to take a while. But the interesting thing about it is that you could take those 3 vertices that are going to be moved up. Like, let's say we have X, Y, and Z. So there's going to be on the midpoint of those edges that are the axes of the cube, X, Y, and Z. They're not the axes of the cube. They're the literal edges that might be aligned with those axes, let's say. in the midpoints of those edges, that we want to transform to create the fivefold kind of pentagonal symmetry of the dodecahedron. One way to do that is to just rotate them and expand them. And the interesting thing about this is that you'd be rotating them on one corner and on the opposite corner, on all the corners of the cube. They all rotate and they all have to rotate in the same direction, no matter which orientation they're in. So that could, so let's say we choose an orientation. We choose the left-handed orientation. Okay, so could this be responsible then for the weak symmetry breaking that is only interested in the left-handed, chiral elements? So that's a possibility. It would also indicate then that all general relativity transformations are chiral. So if we travel faster than light, or if we're in a gravitational field, the bending that occurs in space and time always bends to the left. So somehow there's a link there between the bending, the fact that space-time always bends to the left, like in the fourth dimension, and chirality and left-handedness coupling in the weak force. So that was just what I was thinking about earlier when I was outside having a cigarette while you were, or I wasn't having a cigarette, I was smoking that, but you were right there while you were working on this, while you were doing your presentation, because like I said, time for me is different over here. We have space-time confusion because of the daylight savings. So that's really it. So I'm also working on different things to do with parity in the 120 cell. Getting closer. I mean, I could show you a bit of that maybe.
Okay.
Because yeah, I've been working on it, and it's kind of good. Parity check or hypercube, 120 cell hypercube rotations completed. But the issue here is, well, I suppose I should actually go back and show you the other one first, which is the 600 cell rotation. Is that? Okay, I'm not prepared at all to show this because I was thinking about doing something else today, but so I might have to spend some time looking through notebooks to see which one is which. Oh no, there it is. Okay, I'll present that. So, sorry, screen, share screen. Hide that. Okay, so this is 600 cell rotations completed. Now there's been numerous versions of this. I'll just check to see that I am in the correct one. I have no idea. I'll just run this maybe. Hopefully we don't get a load of errors. Oh, hopefully I'm not overwriting anything. The last thing you want to do is run something that's going to crash the computer as well. Some of these are a bit demented. Okay. Okay, I think we're good. Yeah, there's all the particles in them. Should probably render that in the browser. It might be easier to see. Okay, so these are the vertices. No, these are the generators of the vertices kind of for the 120 cell. although they look a bit odd. No, this is the 600 cell. Sorry, that's why they look odd. Yeah. Then so we have to create those using the even and odd permutations of the generators. Excuse me. I'm not feeling very well at the moment. I've got a bit of a cold, so sorry if I sound sick. Okay. I have no idea what's going on here. I'm just right. So I don't want to run that cell because that's just going to print out what we've got, and that might not be a good idea. I don't think I need to run any of these actually. That says 120 cell, but I think it means. So basically, yeah, that says 120 cell, but it should say 600. So I'll just change that. Now, what's going on? What's happening here is we have we have a bit of a problem because we have the even permutations and just the normal permutations, like all permutations. So I've forgotten which ones have to be even and which ones don't. But let's say it's all of these have to be even. So they're fed in there, and then we take the 100, or then we take the vertices of the 24 cell, add that on top, which is what we're doing here, and then we get all 120 vertices of the 600 cell. And then but what we want to do then is we map all of those to the particles of the standard model. But we need to know which, because there'll be 4 copies of the even permutations, which are the even permutations of S4. So the subgroup called the alternating subgroup of S4, which is A4. Those are the even permutations. But then if we want to convert A4 into S4, then we have to multiply the A4 group by some subgroup of S4, which is just one of the conjugate transformations. So like 1, 2 or 1, 3 or whatever. So we do that. But we want to know like which of the subgroups so if we have these 4 groups, like copies of A4 or S4, sorry, then and each of those has an alternating subgroup because they're all even permutations, then we're really going to wind up with 8 copies of A4. So we need to know which of those 8 copies and which of all of the vertices or symmetry group isomorphisms with the vertices, like which ones line up to which after, so that we know where to place our particles. I'm not explaining that very well, but basically we need a reference frame. So we have our 600 cell and we have the reference frame, because when we rotate, strange things happen. So we need to keep an eye on where everything is lying in the reference frame. It's kind of what we have over here. So there's one 600 cell and a different one. The red one here is kind of a reference frame. It never changes. And then there's another 6. Hang on a sec. Why is it? That's a 24 cell in the 600 cell. There's another one, another one, another one, another one. That's just back to the original one. Then that's all of them without the reference frame. That's with it. So, or actually, I wouldn't even call that the red thing there is not a reference frame. It it is for reference, but it is actually the 24 cell that just corresponds to the bosons, gauge bosons, and then these ones out here are a copy of the a copy of the 24 cell, but they're linked to the leptons, and then these are linked to, let's say, the quarks. So, but then you have two copies of those because you have the right and the left versions, and the spin up and the spin up and the spin down versions. So they'll have another. The yellow ones are another copy of the leptons, but they're spin up, and the purple ones are another copy of the quarks, but they're spin down.
So you are finding the energy levels of this vortex. I mean, is how you come up with the particles. Then you calculate the energy levels of these vertex, and then from there you find out what particles can go there. Is it the way you're doing, or some other way?
Some other way. So, so essentially, we have the 24 cell, and we mapped that using some sort of binary logic, and so we got the S4 subgroups that combine with the octahedral symmetry, full octahedral symmetry, and so on. And then what we do is we know that there's the 24 cell is self-dual, so there's a second 24 cell that's dual to the first. But actually, really, what that self-dual is that you can multiply vertices, like let's say 2 vertices in the dual, and you'll get a vertex in the actual 24 cell. But if you multiply like a vertex in the actual 24 cell with the dual, the other dual representation, which is the binary octahedral group when taken all together, then you'll get another vertex back in let's say the original 24 cell. So it has this kind of gauge boson fermion symmetry thing going on. So like if you have 2 fermions, like 2 electrons, you'll get a boson. So if you multiply 2 matrix elements in let's say the dual representation of the 24 cell, you'll get a vertex in the normal true 24 cell. So that means we have 48 vertices, 48 particles. But those
levels are only implicit. I mean, they don't matter in your consideration of where the particles go.
No, it does matter. So basically, what we can do is we can rotate the dual representation of the 24 cell into the let's say standard 24 cell. But there's 12 ways of doing that, I think. And that's equivalent to just multiplying the alternating subgroup by some element in S4, some transpose element. So 1, 2, or 3, 1, 3, or whatever. So we can do that, and so then we can map all of the any of the lepton groups that we're talking about onto the gauge bosons. So then we can just multiply that by 4 using what I described here with the S4 A4 even transpositions of these to create the subgroups. And then what we need to know, so essentially we want to know if we've got 8 copies of these guys, we need to know which copies fit together. So if let's say there's 24 elements in S4 and there's 12 elements in A4. So 2 of those A4s fit together to become isomorphic with the S4 group, with the total S4 group for those 2 A4 elements. But there's a further 3 of those. But we need to know which of the 8 pair together so that they form their own little groups, and then one of them will be for the up leptons, One of them will be for the down quarks, one will be for the down leptons, and one for the up quarks. We need to know which is which. So the way we do that is with this using, we have a reference and then we have the rotations, and we basically just rotate by 180 degrees, but it's a dual rotation. So it's like a Clifford rotation. It needs to happen in two separate vertices. Why that's the case, I don't know, but it is interesting and it's come up all the time.
Yeah.
These are the results, yes? So this is the 24 cell at the center, which was the red one that I was talking about here.
Oh.
So that's the gauge bosons. And what we see is that when we transform it, this group transforms into itself. So the gauge bosons only transform to other gauge bosons. However,
is it like a decay? Is it like a decay of
when they transform?
Yeah, is it like a decay process or some other process?
No, this is just a group theory kind of. So
because,
this is like a geometric analysis of the structure to see, because we're attempting to apply the leptons and quarks to the A4 subgroups. We need to know which, because we could say, okay, I could apply half the leptons, spin up leptons here, and half the spin up the other half here. But this is also the same as this group. These groups look identical, and this group looks identical to that group. Actually, they all look identical to each other, so it could be any of them. So we need to know which one is which. So in order to do that, I just transposed, like I said, I rotated it by 180 degrees in dual rotation. What we see is that just inverts all the groups. They reverse. But so what I took from this is that this pair reverses to here, and this pair goes to there, and these just switch over. So I take this to mean that these are grouped. Hang on a sec.
You are gauging. You are gauging factor here. You are gauging the things also, right?
Yes, yes. So this is grouped with this. These two are grouped with these two, and that's it. So we're done with the grouping, I think. Oh yeah, and then these two are grouped here, and these two are grouped over here. So that gives the answer. That gives us the answer. Now there's a lot of complicated stuff that needs to happen after that.
You are removing a lot of redundancies in that process, right?
No.
Because when you do permutation, you have a lot of redundancies that come, but you remove that by gauging.
Yeah, I mean, it's one way of looking at it, I suppose. Okay, so that is that. There's a lot more kind of details to go into, but so I mean, another time I can go through this more comprehensively. So now we take the 120 cell. Let's say we've achieved what we were trying to do before. Just as there was 5 copies of the 24 cell in the 600 cell, there's now going to be 5 copies of the 600 cell inside the 120 cell. So basically, we just repeat the process again.
Which one is better, the 600 cell or 120 cell?
Oh, sorry, what was that? Which is better?
Which one is better, the 600 cell or the 120 cell?
Which one's bigger?
Yeah, which one is better?
What do you mean by better?
Better means which one will be more comprehensive. You need to, is the 120 cell transformable to 600 cell? Is there an easy conversion?
But yeah, I just described how that works. So, like I said, there's 524 cells in the 600 cell.
The 24 cell is the basis. So that's
yes. Well, yeah, the binary octahedral group is the basis, but that rotates into the 24 cells. So that's how we get the correspondences between the leptons and the quarks and the gauge bosons. So that's how we were able to generate the 600 cell mapping. The 600 cell fits into the 120 cell 5 times. But it does so in like, I think 10 different ways or something like that. We're not too worried about that.
So 127 is the expanded version, which has the 600 cells in them.
Yeah, exactly. So it's kind of confusing that the 120 cell has 600 vertices, whereas the 600 cell only has 120 vertices.
Oh, it's inversion.
They're dual to each other. Yeah. So because there's,
it's like a inside out type thing, right? I mean, you
yeah,
can think of a simple way of putting a box inside a small box inside a large box like that, right? And then when they do that, then the vertices, something happens to the vertices.
Well, it's more like, let's say you just have a grid pattern. So on the corners of that grid pattern, just a two-dimensional grid pattern, I mean, square grid, on the corners of where those lines intersect in that square grid are the vertices. If you want to take the dual representation of that, you just take the average of the coordinates for those points, and that will give you the point in the middle of the square, of all the squares on all the grids. And then when you join up all of those lines with lines, all of those vertices with edges, I mean, you will get the dual of the original grid.
So if you are putting a square and then in a larger square, small square, but they are not, all of them are not in the center. They are not centric based. They may have their own center.
Oh, they are. They are, aren't they?
A common center. A common center.
Yeah, like it would be like this grid here. And then I draw another line. Oh, and then like this. So there's a grid. But then if I take the points here and here and here, these are the dual points to the original grid. And then I can join those up with the lines. Well, I'll use a different color.
So they are like the representation, the point representation of a line, I mean, of the grid.
Yeah, basically. But yeah, okay. So there you go. So that blue one then is the dual to the original.
Oh, they connect the points that are the representation of the grid, of that particular square grid.
Yes. So something like that might be happening with the 24 cell and the 600 cell, but it could be a bit more complicated than that, because like if you look at that's the confusing thing about the 24 cell. It sounds like when they're saying it's self-dual, that there is another object which sits inside, like the vertices. Basically, so if you look at the 24 cell, it's got 24 vertices and 24 cells. So if you think about it, oh well, then the dual of the 24 cell is just the vertex inside each of the 24 cells. That's not the case. Only the vertices that correspond to the 8 cell sit inside cells, and the rest of them sit on faces of the 16 cell, I think it is. So it's not a true like dual like I just showed you there. Some other dual system. So if this is extrapolated up to the 600 cell and 120 cell, then it could be that some of the dual correspondences are actually sitting on the faces of the polytopes that make up the 600 cell, which I think are tetrahedrons or dodecahedrons in the case of the 120 cell. Okay, so we need to start the process again, and what we do then to do that is we want to go from S4 up to S5, right? Because now we've got 5 copies of S4 inside the 120 cell. So we do that by having a fixed point representation here, and we permute the others, and then we take a new fixed point, which is the number 2, permute the others, then 3, then 4, then 5. Yeah, that's correct. So now we have those S5 representations. We put them next to the particles and coordinates for the 600 cell, excuse me. And then these are the conjugate groups, which tell you how the different groups transform. Now, so then we have to create the correspondences, and what we wind up with is well, here what we want to do is we want to create all the permutations of these to build the 24 cell. We want to create permutations of these generators, if you like, and the even permutation of those generators, with phi being the golden ratio. So then when we do that, these are the even strings, and then we get 384 of the evens and 216 vertices or coordinates for the normal permutations. And blah blah blah. We do some other stuff. Now we create an order group that tells us, which goes up to 41. So this is going to be all of the basically, we know it does get complicated here. So so here we go. We got 24 vertices for this. Now, so when it's got a curly bracket, it means permutation, and when it's got a square bracket, it means take the even permutations of those coordinates. So we want all the permutations of these, all the permutations of those, and those, but only the even permutations of these, and these. But then there's another way to do it with a different set of vertices, which have a different set of even permutations and normal permutations. So we can see here that we have 8, 16, so that's a 24 cell. And then we add on an extra 96, and that will give us a 600 cell, which means the remaining 480 vertices are comprised of these. But we can see that there's another 96 here, so that's an even permutation group. But that's just going to be a copy of this. And this is going to be a copy of that. And this is twice that. So this is going to be 2 copies of this. And these are the vertices. We already have the particles for this. So we have the particles for this one from the 600 cell. Then we have the particles for these, and these. But what we don't have
called snub 24 cell. This is Wikipedia, right?
Yeah.
Why are they called snub 24 cell?
Oh, that's a good question, actually. Because as like, let's say a snub cube would be to chop off all of the corners of the cube, which would give you a rhombidodecaedron or something like that. So that's the same with this. These points, these 8 and 16, which is 24 cell, that 24 cell is sticking out of the 600 cell. It's like the corners of your cube. So when you remove that, you're going to wind up with a snub 24 cell, which is going to have 96 vertices. Just like when you chop the corners of the cube off, you don't get an object with less vertices. You get an object with more vertices.
More, yeah. Initially 8, you have 8, but then when it's snub, you add each one will add another 4, something like that.
Something like that, yeah. Well, yes, exactly, because it's a 4 folds.
When you chop it off, it becomes 4.
Yeah.
So you multiply by 4 essentially. Yeah, multiply by 4.
That's clear. So we have 64, 64, and 64. It's so difficult to talk about this stuff when you're not kind of prepared. But hopefully, anyway, there's a way of dividing these up. Which, okay, so we could say, like, I can drop all of the the leptons, sorry, the fermions in here, and I can drop a copy in here because we had 96, and I can drop 2 copies in here, and we have the gauge bosons here. So all that leaves us with are 64, 64, and 64. But how do we know how to divide these up? You know, that's a problem, because let's say we say half of them are going to fermion vertices, and that's 32, 32, and 32, which when we add together is 96. So that's good. So half of these are going to go to fermions, and the other half, the other 96, will go to gauge bosons. Hang on a sec, is that right? Okay, but we have a further problem, because let's say we say 32. Now 24 of those 32 are going to go to gauge bosons, because it's going to be a 24 cell. That just leaves 8 left over. Then if we do the same thing here, it's going to be another 24 cell with 8 left over, and another 24 cell with 8 left over. Then we add those 3 8s together, we get another 24 cell. So that is 4 24 cells. But again, we have a problem here. We don't know which ones are which. So those are all full permutations. But if we go down here, we see that these are even permutations, and they're even permutations of 32. And we already know that the even permutations have to correspond with the fermions. That means that we have the vertices for the fermions here, which means that the remaining ones have to be bosons, these guys. So this 96 corresponds to half of these, and the other half corresponds to these. So that's probably kind of complicated, but anyway, so the reason why we had to do that was because when we run all of this again and do with the reference grid and the 180 Clifford rotation, we're going to see that the results aren't really what we expect. The groups are more complicated, as I've kind of just shown you. Hopefully I'm not overwriting anything here. Okay, so there's the 120 cell, and it just as a dot kind of matrix, dot cloud or whatever they call it, just a scatter thing. I don't know why there's an error there. Hopefully that error will go away. This is a kind of complicated process here, which takes us quite a long time to run because there's so many. There's 600 vertices, so it's whatever, 600 squared then, because we're going, it's a double for loop. It's kind of a Cartesian product of the two. So and then it has to check each vertices. So check each vertex and ask, is it close to our reference vertex? And if it is, then it's added to within a tolerance, because there's issues when you rotate the 600 cell. It doesn't necessarily come back to the same point. So here are the results. We see that this group of permutations, the S4 or vertices, if you like, in the 120 cell, rotate into itself. So there, this group is there's a word for this thing where when a group rotates into itself. But we know this is the original 24 cell that we were working with, that everything's began with. So those are the first gauge boson set. This group up here,
self-image, right? It's not self-image.
Sorry?
It's not self-image.
Could be something like, yeah, it could be something like that. I was looking at a video, and they were talking about different subgroups, and well, yeah. So it's a big part of group theory anyway. So here's 96. 96, and here is 196, was it? 192, right? Sorry. So those are those groups that we saw here: 96, 96, 192, and same up here. In fact, I think we might be using this group. Yeah, we are. And then so this is 64, 64, 64, but you see that when we rotate them, okay, this is inverted, and this is inverted, and this is inverted. So we can do the same thing that we did previously and just say these two move down here, and these two at the end here move in here, and same of everything is just switched around. But if we look in here, the situation is far more complicated and more chaotic. Oh, so that didn't work. That did not work at all. Okay. Let's reset and zoom. Oh, it's doing something funky on the zoom. Let's just ignore that. There we go. It should work. It's a bit difficult to get it exact, but so these are the groups down here, I believe. And each one of these is a S4 group. So half of these should, is it half, or half of them should correspond to bosons and the other half to fermions, but I could be wrong about that. It's a little bit confusing. So 8, so 16 by 2, 32, but half of that. So we get 16 here, and then we want to take 8 from here. So that's a 24 cell, then another one, then another one. That's 3 24 cells. And then we take 2 more. So that's 5. Okay. So it's 5 24 cells. So altogether, it is a 600 cell, which would mean, oh yeah, but we have to remember that this group here is 96, but it needs an extra 24 cell. This group here is 96, which also needs an extra 24 cell, and then we'll need 2 for this. So that's we already have one there, so then that'll be 3. So we'll get. Hang on a sec. Why is this so difficult to remember? Okay. Oh, so we got 1 here. That'll pair with that. Then we need another 3.
They're not chiral, right? No, not chiral pairs.
Don't ask that. Oh, sorry. I'm just need to get my bearings on this. Should probably write. I'm sure I've written this down somewhere, but I cannot remember. 24. Anyway, trust me on this. There's some relationship there. So anyway, we can see that when we rotate it, it's pretty chaotic. There isn't really, okay, this one goes to that one and that one goes to that one. So that's good news maybe. But everything else is just a lot of chaos. And so the way to examine this then is to do this parity check thing that I'm involved with here. Basically, we do the same thing again, but we're taking note of the parity, whether even or odd, in the S4 subgroup or in the S4 group, and then we do all of our calculations for the vertices.
Vertices, the parity you are doing with vertices or the
parity is just the even or odd transpositions of S4. So then we have some strange things happen here. When we count, you see we have 32 evens, 64 total. 32. So these are the groups we're talking about. So this is correct. It's a bit odd that we've got, assuming 0 is an even parity, which it is, I think, in this case. This shows that we have 14 evens in the 24 cell, which I don't think is right. But everything else is fine, so we're just going to ignore it, which means, of course, we have 10 odd parities in the 24 cell. That's a bit strange because the 24 cell and S4 are isomorphic, and I'm fairly certain that the parity in S4 is an even split, so 12 both ways. So something odd has occurred, but we can kind of ignore it for the time being anyway, I hope. So these are the results then. We have 8 even parities of this element in S4. 8 and then another 8 here, which is also even. And then we have 16 of these, and there's 2 of each. So that's 32 again. So this section here is 32, and this section here is 32. And half of these will be gauge bosons, let's say, or fermions. So that's 16, and that's equivalent to the 16 vertices of the 16 cell. And then the remaining, then we just take one of these, the remaining 8, which is the 8 cell of the 24 cell, and then we get a full 24 cell. But we could take half of these, so we could just take 4 of these and 4 of these. Well, if we're talking about fermions, because this is the even group, then that leaves, the other half for a different group, which might be a better way to do it. So it's just difficult. We don't actually know which ones correspond to which, so we'll have to go through here and maybe count the differences. So yeah, that's it. So that's where I've gotten to so far, and I've also done some I've had to change some of the, for instance, these are no longer gravitons, but they're the leptogenesis particles. And I also had to reorder some of the gluons and reorder the leptogenesis particles based on the 6-2 split of the gluons in the Gell-Mann matrices or Gell-Mann matrices, and applying them to the 6-4 split or 6-2 split of the S8 matrices in the 24 cell isomorphism that I already spoke of. So that's really it. That's all I have to show you.
Do they go inside out, these cubes?
Yeah. Yeah, the smaller cube will go to the outside, and the outside will go to the inside. But this is only a subgroup of the 24
transforms occur. They create the transforms, right? They go inside out.
Yeah, if you rotate this in the 4th dimension, this will.
But the inside one goes outside. Outside one goes inside. Is that possible?
Correct. This is only a subgroup of the 24 cell. So if you actually were to rotate it, Well, it depends on which direction you rotate it, but the particles would change in the group. So let's say the leptogenesis particles would disappear, and instead you get the other gauge bosons would appear. But there's something about this. I was looking at it, and I just wonder if, because you've got the gluons, which are kind of in the nucleon or the nucleus or whatever, nucleon, I guess, but then they're so kind of symmetrically tied to the leptogenesis particles. It does make me wonder if some of the leptogenesis particles might still be kind of lurking inside the nucleon, sort of self-eradicating or whatever, even generating the quarks over again. But that's probably wrong. But it also might account for maybe some of the missing matter that was a problem that was kind of solved by that. I suppose that's solved.
Connection between the gluon and the quarks, right? The quarks can become gluons or vice versa, something like that.
Right. Yeah, they are the force carrier of the color charge. So as the charge.
Yeah, but the quarks, the gluons itself, are some connection with the quarks itself. I mean, they are interconnected somehow.
Yeah. So I think the strong force binds the quarks together inside the nucleus, the confinement, but you can't have a single quark.
The gluons are some way you can derive from quarks. Is it possible to derive the gluon aspect, or are they separate entity? Are they separate entity?
Well, it'd be similar to how the electron has a charge, and then so if it interacts with another electron, there's the force carrier between them is a boson called a photon. So I think it's the same thing with the quarks, because they're confined closely in the nucleon, that they interact with each other, and the interaction between the two of them is carried by the gluon. But the gluon also is responsible then for the color charge. So if you had like a red up quark interacting with a green down quark or something, then it would share like an anti-green gluon, and that gluon would pass from one quark to the other and then interact with the green gluon, and so the green and the anti-green would cancel out, and then you'd get oh no, sorry, let's say that the first one was red, and it would an anti-red one would leave, which would change the red to blue, let's say. Something like that. Anyway, I'm getting confused, but then no, actually I think I had it right the first time, but basically that's how it works. There's this SU3 transformation going on, so it's all described by that. But you could just do it with an SU2. You could just literally do it with the SU2 subgroup. So basically, if this is the 16 cell subgroup of the 24 cell, you have in the cells here, you have 8 more vertices that are possible, and that creates the 8 cell, which is basically a hyperoctahedron, I think. And that hyperoctahedron can be transformed in such a way that it produces the exact same results as SU3. So you don't actually need SU3, I don't think. Also, if you look at how SU3 works, like if we want to create the invariant rotations of the SU3 group, if we want to do it with SU2 or with SL2C, we're going to need to do the dot product. We want to multiply the matrices. But if we want to do the same thing with SU3, we're going to have to sum the values. And that, I think, is a bit odd. They both should be multiplications, but it doesn't work if you take the dot product. You don't get the rotations back. It only works when you sum them. So I think there's a problem with SU3. I don't know why people don't talk about it. And so I think you could just replace it with an SU2 group.
It's like a pseudo thing, I think. It's like a pseudo structure.
Oh, yeah. Well, the result of these things we were looking up the other day, like pseudo scalars, and remember, and
yeah,
and I did look up a pseudo scalar, but I remember I was thinking that it might have to do with the quark. What's that thing called where you have? Is it the eightfold way or something? Eightfold way.
Yeah, the octet.
Yeah, of quarks.
Oh, sure.
With the mesons, wasn't it? Oh, great. Mesons, and I pointed out that the strange there's these axes that are strange. Wow, the search is really bad on Wikipedia. Mesons. There we go. So these axes, which are the strange, and it's like +1, 0, and -1.
Yeah, I showed it.
That these were the pseudoscalars because you know that it's a scalar value, but it corresponds to something which isn't a scalar. But that was wrong. But it wasn't too badly wrong because the pseudoscalar is some sort of transformation which would just take +1 to -1. So essentially, it's a rotation, or a translation or reflection, which would take this kaon to this kaon. So +1 to -1. So I wasn't too far off in a way, but I was a bit wrong. Also, we made a number of other kind of errors. Well, I think remember we were looking at some sort of U sub A matrix or something. We were wondering what the A stood for, and I think you said anti-diagonal, and I thought it might be anomaly or anomalous or something, but I don't think either of us are right. I think it might stand for ancillary or ancillus, just like another. But anyway, these are kind of details anyway. I think there was also a thing where, well, it would be handy if we could go back to parity, wasn't it? Were we in parity? No, it wasn't. So there's pseudoscalars again, you see? +1 and rotationally invariant. And then we have a lot of these irreducible representations.
The top quark is the highest energy, right?
Top quark, yeah. Yeah, I think you're right.
It can decay into all this.
I don't know. Can certainly decay into a lot of things, yeah. Fermions.
A recent one, I think LHC, they tried to find the top quark.
Alexei.
Yeah.
Alexei who?
The hadron collider.
Alexei?
Yeah, LHC, yeah. The
LHC, right.
Yeah,
LHC.
Yeah, LHC.
Right.
There was some article recently I read about a top quark. They're trying to time aspect. I was considering that.
So yeah, we were looking at this
flavor
symmetry, and quantum chromodynamics. I think we were in here.
Identification we need. I think there are some confusion about this.
Because we went. It was all about mass generation, wasn't it?
Like
the symmetry group. So there must have been. This is it. U1A. So I'm thinking is symmetry is anomalous. So I thought A might stand for anomalous, but it was. I think it's actually ancillary.
Auxiliary.
No, kind of like ancillary, but they just say ancillus. And then I think we said this one was the vector or something. subgroup. This is left and right. So these are the cosets that we were talking about.
They're left and right. Cosets.
Yeah. So cosets are interesting. Like if you have all of the integers.
Is it left and right chiral things?
Why do you keep asking that?
No, I'm saying that are they like chiral cosets?
Yes, of course. Yeah. But so the cosets are interesting because you could have, like, let's say you could have a set, like a subgroup of all the counting numbers, which are just the even numbers. And then the coset of the even numbers are just the odd numbers. Or in other words, shifting the even numbers back 1 or forwards 1 or forwards 2 even.
Oh.
So it's kind of, yeah.
Shift operator.
So this would be the left-handed ones and the right-handed ones. It seems to suggest that you could shift one into the other somehow. I don't know how you do that, but
yeah, they are mirror, right? They mirror, some mirror operation.
Can you turn a left into a right via? Yeah, of course. There would be a mirror operation. Yeah, it would be just a reflection across some axis. Okay, so it's interesting. There was a couple of other things that I thought we got wrong. There was a lot of this stuff about diagonal matrices. We made a lot of comments about diagonal. So there was the pseudo-scalars. There was things that were diagonal and then off diagonal or something. Non-diagonal part. So I was thinking that the non-diagonal would be everything that isn't on the diagonal, basically. And so usually you'd have like whatever's on the diagonal are the real values, you know? So that becomes the mass. I think maybe you take the trace or something.
Yeah, you can do Hermitian and do.
Yeah. There's the coset space. So technically the spontaneous broken chiral symmetry generators comprise the coset space. So pretty sure, did we say that this was vector for vector space? So basically we have this times this, and then this is, I think this was less this something. I figured that out. I've forgotten what it is, but I guess it's not important. This space is not a group. It consists of 8 axial generators.
What does V stand for? Vector?
I think this is the total vector space, right? Why is it
space like a splits into the left and the right?
We figured that out, but I can't remember what we said. Yeah, it splits into the cosets of the left and the right. But so I figured this part out, but I've forgotten it. It was this group. See, if you add these two together, it's going to be as big as this group. So if you remove this from this, you're just going to have 0, you know, because this group is as big as these two combined, I think. Unless this cross means that this group is even bigger than this group. Now I'm getting confused. That's not good. Okay, so yeah, because there was a lot of stuff about diagonals and non-diagonals.
So I mean, which would imply it could go out of the vector space if you do that.
I don't know.
They may not be confined within the vector space. L and L, when they
do
that.
It's a group. So yeah, that's a good point. No, it doesn't really mean that, because you could just have copies of copies. So yeah, because it's a group, so it has to be closed. Can't go outside of itself, or else it's not a group. But you could multiply everything by some value or something like that.
I mean, you can talk about the chord plasma confinement and use this one and say that, you know, what we see in the, you know, the strong thing, it can go out and become the fermion. They go outside, and they create the atom, so you have the nucleus inside where you have confinement, and then that vector space you somehow dissociate the left and right, and they go out of confinement, and that creates the fermion outside, which creates the weak force.
Yeah, maybe. Another thing I was looking into was this introduction to symmetry group SU5, because this SU5 symmetry group was, I think it was proposed by Glashow and someone else. Georgi and Glashow, 1974. It was supposed to be a grand unified field theory, wasn't it? So it would.
Georgia was the person, one of the Nobel thing, right? Was he one of the? With
I don't know. Probably Glashow was as well, was he? I assume.
Yeah.
Salam.
One of them are associated with these people.
Yeah. So the idea, this was another point in the standard model. I think I was saying SU2 for the weak force, U1 for the electromagnetic force, and SU3 for the color charge, but that's not right. U1 here stands for the hypercharge, which makes things more complicated. But yeah, there's a whole reason why that's the case. So
it's a charge group, right? You make it, the U1 is a charge group.
Yeah, it's hypercharge. Hypercharge.
I just charge for the leptons. Put the charge for leptons. Is it right?
The lepton. Yes, that's correct. So, right, the simplest group that incorporates this as a subgroup is SU5. As will be shown below, this group has irreducible representations of dimensions 5, 10, 15, 24, 35, 40, so on. Before discussing the details of this model of unification of the three interactions, which was proposed by these two in 1974, it is expedient to establish some basic mathematical properties of SU5. SU5 is a special case of general groups SUN that are formed from unitary n-by-n matrices with determinant 1. An arbitrary unitary matrix can be represented in terms of an exponential of a Hermitian matrix H hat. So here we have the exponential of this matrix, and
yeah, the conjugate is the same as the
inverse, the transpose conjugate.
That's the property of the
transpose conjugate, isn't it?
Transpose.
Transpose, yeah. Okay, so but this is pretty weird. We have the exponential of a Hermitian matrix. So if the matrix is diagonalized, so it's just, see that was another point we were making here, that when they're talking about diagonalized matrices, are they saying like, I think they talk about diagonalized matrices here somewhere, but you'd wonder, are they talking about matrices that are zero everywhere except for the trace or the diagonal? Yeah, but I don't know if they are saying that. So that's anyway. But if we take we want to take this this exponential, and this is diagonalized, then we just take the exponential of the diagonal components, and then the trace of that, I think, and then we're done. But not sure how to do that for all the other kinds of asymmetric sort of matrices that you might have. Okay, so it's called a generating matrix of U. Right. The multiplication of two matrices corresponds to the sum of the infinitesimal Hermitian matrices. So it kind of goes on like this, and it's very opaque. And you see, I'm not So SU5 predicted that the proton would decay. This Gus theory, which apparently they don't expect the proton to ever decay. So, and there was a couple of other reasons why this might have been ruled out as well. But ultimately, Galasho and George, said this doesn't work, so don't bother with it. But there's still a lot of people who do bother with it. Like they have it as a smaller part of other bigger theories where they're trying to unify things.
Because they are traceless or something.
Is that why the proton decays?
Yeah, proton doesn't decay, right? Because it's traceless, something like that.
Well, would it be traceless? Why would it be trace? Surely the proton has mass, doesn't it? Hello? Well, the word traceless appears here on this page, but other than that, to construct. You still there? Are you still there? Yeah, you're muted though, Rajan. You're on.
Yeah, I had something coming on. I didn't want to put the phone. Yeah. So what I'm saying is that trace means it has a zeroing in there, but traceless means there is no zero.
Well, traces. So wait a second. So if we take the trace of a matrix.
Yeah.
Does traceless mean that its trace is zero?
Yeah, I mean there are roots. You can find the roots of the.
No, not the roots. I'm talking about the trace, which is the sum of the.
Some of them equal to some zero thing. You can connect to a zero matrix or something like that.
Zero matrix. What's that?
I mean zero. The vertices. I mean if you multiply that, you can equate to a zero row, zero column, and you can solve that problem. Something like that. The trace is something to do with that.
Well, the trace is just the sum of the diagonal components in the matrix. Well, what a traceless matrix is, I've forgotten.
Again, I was looking to trace.
See, these are not. Just want a definition of a traceless matrix.
Yeah, trace is a.
Any trace zero matrix.
Trace zero is a commutator. Yeah.
The only information
that dot product, from the dot product, then they are
the sum of the eigenvalues is zero in a traceless matrix.
No, the only information you get from the matrix being traceless is that somehow the eigenvalues. Okay. The eigenvalues are the diagonal terms, right?
What?
The eigenvalues you solve for the.
Yeah.
I actually I did that in my thing. But
yeah. Well.
You put lambda and then equal to zero.
Eigenvalues of a matrix.
It's actually like a trace. Yeah, I think it's like a trace in that sense.
It does, but if you want doesn't it give you like
you put a lambda there and then solve it. Put a lambda for the diagonal terms and solve for lambda.
Yeah, I know, but
yeah, see minus lambda for the diagonal terms.
You stick them into the yeah, we know that. We don't have to like repeat all of the stuff, but yeah, I suppose it doesn't really matter.
The trace, yeah, you equal to zero. That's what I mean. So that's how you get the eigenvalues. But the trace, we
still didn't find out what a traceless matrix was. So
trace of a matrix. I'm saying the trace of a matrix is right there. It's defined as the one before. You had it above the trace.
Well, we know what a trace is. It's just the sum of the
eigenvalues.
It's just the sum of the diagonal components.
No. You solve for the eigenvalues using the lambda,
Yeah.
And then the sum of that lambda is the trace. The lambda is the eigenvalue, right?
Some of the, yeah, because the eigenvalues.
And then you sum up all these eigenvalues.
Yeah.
That gives the trace.
Right, but we're asking what a traceless matrix is.
So they may not, traceless is when they go to 0.
Yeah.
When you sum it up, when you go to 0, that becomes traceless.
Yeah, I know.
When you put all the sum of the eigenvalues.
What point were you trying to make about traceless? You said that was the matter or something, was it?
Yeah. So when the sum of all the eigenvalues goes to 0, it becomes traceless. And then what does that mean? That was
well, you just asked. You said that something about massive particles traceless or something. You asked something about the mass, was it?
Yeah. So it becomes, for example, if you say photon.
No. What was your question? No.
The question is that it becomes massless. It decays.
That wasn't well. Yeah, it wasn't what you asked, but I don't know. I mean, if the mass is on the trace of the matrix, and the trace is 0, then it has no mass.
Yeah, like photon, for example, you can say is photon traceless. So you can figure out whether the photon has mass or not based on that finding the trace.
Yeah, that makes sense. Okay, thanks for that. So let's continue on. This is achieved by. So we see all of this kind of stuff. Oh yeah, we were talking about SU5 and whether you asked was the proton traceless. Now the proton can't be traceless because it has mass. Okay.
Yeah. So it's photon, not proton. Photon can be traceless.
Oh. Right, but we were talking about protons.
Proton.
We were talking about protons and about whether they decay or not. So maybe you meant if they decay, they are traceless, is it? Because
yeah.
I don't know about that, Rajan. I don't think so.
Yeah, that's the whole question. We don't know.
Okay, so
the proton has to
way through photons, because then we're just, when we're chasing our tails, okay. Since the unit matrix commutes with any matrix, the commutation relations are the same for the matrices of the SUN. So
there's U5 also, huh? U5 for the SU5, the U5 generator. What is
I don't see phi. I see SUN. Do you mean phi is an N?
U of phi. U5 is for what? U5 generator.
I don't know what that is. U5.
Yeah.
You say? I thought you were saying phi, like the Greek letter.
U5. Yeah.
5. Yeah.
What are they for?
What?
What is the U5 for? Who do they associate?
Yeah, it's a good question. Well, so the special unitary group has what? Determinant 1, and the unitary group doesn't.
No, U5 is a generator, right? A charge
U5,
generator.
U5, the 5, not U5.
Are they charge generators? The hypercharge, whatever.
Are they hypercharge generators? Oh, I see what you mean. Yeah, because of the U1. Oh, that's a good question.
U1 becomes U5 on the central circle.
Unitary and what's a unitary matrix definition? You see, this is it. This is what I don't get, because you have U5 and you have all of these groups like U10, and they go on forever. I don't really know what they are. I've yet to. I assume U1 can't. Oh well, if U2 would be what? All the matrices, all the unitary matrices of 2, yeah. So U5 is all of the unitary matrices that are 5 by 5, right? So this is obviously one of them here.
So you have everything 0 except 1.
Oh no! Well, what's the definition of a unitary matrix? Are their rotation matrices
becomes 1, right? Determinant is identity matrix. You get If you take the inverse times the thing, multiply it, you get it. What I mean is the unitary is
it's right there.
Determinant of 1.
Oh, okay, yes. Equals its conjugate transpose. Is that the only definition though, of them?
No, unitary matrix defined as it has a determinant of 1. It is a matrix of determinant 1.
Okay, so what's the difference between that and a special unitary matrix?
Okay, special SU, SU, right? SU matrix versus the unitary matrix. So that's a special form of unitary matrix. SU.
Yeah.
And
what's the special part?
There, I think it's a Lie algebra. It is connected with Lie algebra, I think.
It is indeed. Yeah, so I suppose that's not that interesting. It's just a rotation thing. So
yeah, so you look at that special unitary. Let's go back to a definition, the Wikipedia.
Oh yeah, good idea.
So we'll clarify that. I mean, I don't remember, but I want to ensure that.
Unitary matrix, because I think it's something to do with the fact that it has determinant 1, but it seems to be a complex matrix U is special. Oh, there it said it there. So special unitary has determinant 1. So these guys,
complex.
It doesn't matter whether it's complex or not. So these guys are unitary. So this group here, the special unitary group, is contained within this group. I'm pretty sure.
Yeah.
Okay.
The larger definition. This is the larger definition of the.
Okay. From the constructed Hermitian matrices, the diagonal matrices of the following form. They are already Hermitian. Altogether, there are 5 squared, 25 generators. All right, so this is how to construct some generators of the SU5 group. Then it goes on and on like this. And then it comes into these representations. So to determine the irreducible representations of SU5, it is convenient to use Young diagrams. In terms of Young diagrams, an irreducible representation of SU5 is described by at most 4 rows of boxes, one upon the other, where the length of a row is required to be no greater than the length of the preceding row. This convention, the fundamental representation corresponds to a single box. An irreducible representation of SU5 is labeled by 4 numbers that specify the number of boxes in the 4 rows of a Young diagram. Okay, so most commonly the combination such is employed. And these are some important representations. Dimensions of an irreducible representation of SU5 is evaluated as follows. First, draw the corresponding Young diagram twice, one above the other. Then fill the first row of the upper diagram with the numbers 5, 6, 7 from left to right. The second row of the diagram, start on the left-hand side with 4, 5, and in the third row with 3, and the last one with 2. 5, 6, 7, 8, 4, 5, 3, 4, 2. And then next, write in each box in the lower Young diagram the integer that results from summing the number of boxes further to the right and below plus 1. Finally, multiply all numbers of the upper diagram and divide by the product of all numbers in the lower diagram. Example. Oh, here we go. Evaluate the dimension of the irreducible representations of the SU5 group given the following Young diagram. Okay, so we saw that. So basically, like they said, they just multiply all of those and divide by all of these. How do they get these ones again? Next.
What is the logic? How do they get 5, 6, 7, 8 and 7, 5, 2, 1? What's the logic?
Yeah. I think the logic is because these Young diagrams is for SU5. So it's 5 by 5 matrices. So you start with 5. And then you go 5, 6, 7, 8, 4, 5, 3, 4. So you're kind of you're counting up but you're also counting down this way. See what I mean? So this is gonna be, if this was a square block, this would be 5, 5, 5, 5, and 4, 4, 4, 3, 3. But so they're just taking. See, this is it. I'm kind of Young diagrams are kind of strange.
Keep out separately, I think. Anyway,
yeah, there's some strange reason why this is the case.
I want to derive these things, get a better understanding.
Yes. Next, right. So this part I don't get down here as much.
But it's very important to our advancing theory. I want to get a better handle on this.
Absolutely. Next, write in each box of the lower Young diagram the integer that results from summing the number of boxes further to the right and below plus 1. Further to the right and below plus 1. What does that even mean? So this would be I don't know what that means. So
now, how do they get 4 at the bottom? I mean, 7, 5, 2, 1. Then they have 4, 2. How do they derive that? I think that's where they're trying to describe.
Yeah, it says it here, from summing the number of boxes further to the right and below plus 1, but I don't know what that means.
You have to figure out.
Yeah,
so decode that.
Well, that's what we're trying to figure out. That's why I'm looking at this. So
yeah, they're not written, very expansively.
I agree. Yeah. I mean, we could look up Young's diagrams, which I have tried to do in the past, but
oh, you use them, right?
No, I don't. Well, I've looked into them, but see, like if I were to click on this video, and if we were to watch that video,
right. There's some people who describe them nicely. I mean,
they tend to be these videos tend to be quite good, like explained very well, but they're also extremely basic. So this is just the partition groups. 3 can be partitioned as 3, 2 plus 1, or 1 plus 1 plus 1. So that is where we get these boxes up here. So you could have a group that's partitioned as 1 or 1, 1, 1, 1, I think, or 2, 1, 1, 1, or it could be the other way around. So they'll draw the boxes next. Yeah, so 3 is just like this, 2, 1, and 1, 1, 1. Okay, so we had it right. So you see how basic this is. But he is making a point about an important rule here.
Greater than the other one. If they have the same length, and we compare the length of the second row and so on. So here, this one is greater than this because you have a row of length 4 and a row of length 3 here. Same argument here.
Okay, so that might be. Well, why is this one bigger than this one? Oh, because this row here is bigger than that row. Okay, so you see
a row, converting the row into a column.
We already know that the conjugacy classes of Sn
so the row becomes the column.
Here, 1, 3, not 1 cycle. It's 1, 2. Here, it's just 3 1 cycles. So that's just the identity. Now we found the.
Oh, that's the vector.
Conjugacy classes.
Raw vector.
No, these are permutation groups, aren't they? This is
they're decomposed, right?
No, they're symmetry groups. This is saying 1 goes to 2, 2 goes to 3, 3 goes to 1. So it's a cycle. So it says that there SUN are determined by cycle structure. This is a transpose. It just says 1 goes to 2 and 2 goes to 1, and 3 doesn't go anywhere. And here 1 goes to 3, 3 goes to 1, 2 is the fixed point in that. And then the identity is just the identity. I don't know how to write that in. Oh, it doesn't have a cycle notation structure or conjugacy or whatever. Well, these are the conjugacy classes for SU3 can be written as Young's. All right, so that's interesting, isn't it, Rajan? The conjugacy classes of a symmetry group can be written as Young's diagrams. Then that kind of implies that these Young diagrams are actually conjugacy classes in some sense, which is exactly what I'm doing here. These are the conjugacy classes of S5.
So are they like a Young diagram?
Yeah, these would be basic. This is just the more explicit way of writing it out. These are all the conjugacy class. So here's 5. So that would be 5 boxes in a line, kind of 3, 2. It'd be like 3 boxes in a row with 2 underneath, or the other way around. You know what I mean? The 1, 1, 1. Actually, that would probably be. Oh, wait a second.
The column.
Yeah.
Column matrix.
I don't know. I think we literally just saw it in the last video. Yeah, the column. Yeah, you're right. The column that's the column 1, and then you'd have 2. So this one is bigger than that one. Remember they said that? That this one, because 2 is bigger than 1. So, and we can see that this group is bigger than that group. And this group is bigger than the first group, so on and so forth. So these are just conjugacy classes using Young's matrices. So I think so kind of part of the reason I'm looking at this is because I want to see if what I'm doing is, you know, I don't want to get to the end of the work and then find out that I've been doing it wrong the whole time or something. But I don't think I'm quite on the level of all of this stuff. But essentially what this is seems to be saying is that these are just conjugacy classes for SU.
Find the dimensions.
Yeah, the fundamental representations, right, which would be the conjugacy classes, I guess. So that's interesting.
I'm also interested in the dimensions, remember?
What do you mean?
Yeah.
What do you mean?
The actual calculation of the dimension. I may come back to that. Calculation of the dimensions.
Are you talking about this here?
Yeah. Like each of the groups, when you put in the groups, what kind of dimension they get. So this is for dimension 5.
Why do these both have dimension 5? The representation. Is this the identity? How does that have a dimension of 5? It looks like it's just 4. Fundamental representations.
That's why it's not directly related. See, the matrix, the elements of the matrix directly does not give what dimension it has. It's a calculation you have to go through.
Well, if you go back to this here, did he ever have 1 box? Well, so this has 3.
That's a dimension. What is the dimension? Is it a dimension related to how much they can be represented by? Or
what does that mean?
So like the path of 4, it has 1, 2, 3, 4, 5 of them, right?
Well, 1, 2, 3. This is 1, 2, 3, 4, and it's got
but it has 5 possibilities. The partitions of it's like a partition. Partition of
4. It's partition of 4, and it's got 4 elements in it.
No, but there are 4 ways of partitioning it.
There's 5 ways, is it? 1, 2, 3, 4, 5
ways. 5 ways of partitioning it.
That's a very good point.
So is the dimension related to the partitioning aspect? That's the question.
So the dimension of the partitions is just the number of conjugacy groups. Then why does it say this one? No, maybe it's because this is 1 and this is 4. So together they have 5 dimensions.
No, both have.
Both have, yeah, it does say that. No, but it says the representations of this and this both have 5. So the representation of this, whatever that is, and the representation of that have 5 dimensions. Yeah, so that's what you were saying. But that's not the same as saying that the overall conjugacy group of whatever this is has 5 dimensions. Is it? 1, 2, 3, 4, 5. So 1, there's your 5 dimensions there. And there's your 5 dimensions there, yeah? Because when we do this calculation, 5 divided by 1, we get 5. So that's 5 dimensions. This has 15 dimensions. This is 10, and this is 24.
So is that partitioning? How the partitioning works?
Yeah, these are the partitions up here.
So you have to calculate for the partitions, the dimension.
Yeah. And the partitions are just
the partition, and then from the partition, you can calculate the dimension. Looks like.
Yeah. Which is just the size of the conjugacy group, isn't it?
Seems like, yeah. So you have a numerator and denominator.
Yeah, because if we look at okay, well, I mean, we can look at subgroups or something.
You can say, how are the dimensions related to the partitions? Something like that you can ask.
How are the dimensions related to the partitions? They are. I think it's the size of the group.
Conjugacy group.
Yeah. So that would imply. You see the way here we've got these are the partitions or the conjugacy groups, and then the formula to get the size is this, which looks identical to this formula, right? Because this is a factorial.
This is a Young's diagram that's using. But the other people are using something else.
Exactly. Formula for the size. So these are equivalent to the other things. And then, so if we get the size of the conjugacy class, we get 1, 15, 40. So I think that's equivalent.
That's the dimension.
Exactly. Is there anything else we need to look at here? Irreducible, trivial. Now this one is interesting, okay? As we go down here, we have irreducible representations or whatever. Now this is what I find. So these conjugacy classes up here are the irreducible classes, right? According to this, because they keep on referring to them as irreps, don't they? Irreducible representations, which are irreps or something. I can't find the word, but irreducible representation. Okay, so if we go in here, these are the irreducible representations supposedly, and then the trivial ones. Well, you all just get 1. There's there's the groups, and then we have sign. So this is basically whether they're even or odd parity or whatever. And then you can, then there's something to do with standard. Forgotten what that is. So then, but then you can multiply the standard by the sign. So, and then that just inverts the numbers. But then you have things like other 5-dimensional irreducibles. So 5-dimensional irreducible, and then you have it again. A 9-dimension irreductible. That says irreductible, but I think they mean irreducible. No, that says irreductible as well. I think it's the same thing. Irreducible and irreductible. We should check that though, maybe, should we? Irreducible representation. Did you mean irreducible? Yes, I did. Perhaps that's what they meant as well. Okay, so I think that's just a spelling error. Yeah, there's something about this though that's related to the theory of everything that I'm working on, and the fact that, because this is symmetry group 6, right? So that this contains S5 in it, which is what we use to generate this thing and this. So there's
at one point I calculated you need S8 or something like that. You need a minimum to have
S8,
all
S8 was there. That's useful for the chiral part of the 24 cell to show how the weak force binds to whichever thing. But yeah, so there's irreducible representations. Okay, we'll move on then. I think we've got a handle on that then. It's just a different way of doing what we're already doing. Boxes, for example, the representation stands for the symmetric product of, okay, and then the product of two representations on the
so
other.
what is the irreducible representation? What did you have there in the
oh, you want me to go back to this?
The irreducible. You had you have searched about irreducible representation.
I looked up irreducible.
Irreducible. It's not irreducible.
I said, if you look here, it says irreducible.
It's not irreducible.
It is irreducible. It's meant to be irreducible. So I just checking to see if irreducible and irreducible are the same thing, which they were, because this is a typo. It's a typo. So yeah, anyway, there's more to say about this thing. For instance, the 16-dimensional part here is probably the 4x4 tensor spacetime. You know that spacetime tensor with the 16 dimensions. What is it called again? Stress energy tensor or whatever.
Yeah.
And then there's something about the gravity. You get this 9-dimensional irreducible thing going on with the gravity, and then it breaks down to 5, which is the massive gravity possible idea, and also just all of this, the fact that it's got S5 in it, just these 5 things that then conform to all of these, and then the what you call it, the dual of this then is the 600 cell version, wherever that's gone. Oh, it's here.
I mean, I wonder whether it's connected to diffraction versus. See, if you do a diffraction.
No, it wouldn't be you can't do a diffraction though, because this is already
diffracted.
Well, it's not a real thing. It doesn't really exist somehow. It's like a platonic solid, like it's like an ideal form of the. This is some sort of space, like a spin space, where if you reflect it, you're gonna transpose like a anti-tau right-handed to a anti-tau left-handed. Do you know what I mean? So you'll just get the right and left-hand version. If you reflect it in a different across a different axis, you're going to get the right-handed tau. And if you reflect, so yeah, it'll convert like matter into antimatter without changing the spin or whatever. So it's a very basic concept, really. And then it'll do that for all the different kinds of things. But it could also, so the question is, it's basic on that level, but does it get more complicated? But I think that the main thing is how it's supposed to unify all the forces into a group. just like SU5 is trying to do. Okay, so any product of two representations, on the other hand, may be decomposed into irreducible representations, forming all combinations of boxes of the T-ring diagrams. All columns that contain 5 boxes are simply ignored. So just by this is equal to that plus that. And we have some sort of associativity thing going on. And then that equals that. So these reductions are often expressed in terms of the dimension of the representations. Oh yeah, so just like we saw earlier, this is the 5, this is 5, this is 15, this is 10. So 5 by 5 is 25, but it's also equal to 15 by 15 plus 10 is also equal to
partitioning, right? Yeah, partitioning. Like partitioning of dimensions.
Well, these are the partitions. And then the size of the partitions are dimensions. The following we suppress. Okay. So here it goes. Embedding SU3C, which is the charge, SU2L, which is the left-handed weak acting leptons, and SU1, which is the hypercharge. So you see that it's fairly limited compared to this thing, which is like it doesn't just deal with left-handed. It also has right, and it also has spins, and I'm assuming the other one has spin up and spin down. Okay.
Oh, the spin charge and
yeah, the color group, the group of weak isospin of left-handed particles, and the gauge group U1 of the weak hypercharge. So not of the electromagnetic charge, which I was getting wrong. Simply, you need to enumerate the Casimir operators. Well, really, which were these guys, weren't they? This is indeed Casimir. Yeah, invariant, easily proved. So it all equals 0 or something.
What does the C stand for? Combinatorial.
Sorry, what?
What does C stand for?
Oh, they're the matrices, aren't they? In this group or something. Remember we were looking at those.
Go up.
Yeah, here they are.
Where the first?
No, yeah,
the first definition.
Right, such a matrix where the element value 1 is given the intersection row as this. It is rich. So the simplest representation. So these were the U1, U5 matrices. Seems to be C, this kind of thing.
Oh, they get the identity matrix by intersection of the row and column, something like that.
Is that what we're doing here?
Matrix element value 1 is given by intersection of row alpha and column beta. That's what C is defined. So they get you get the matrix value of 1.
Oh, okay. Yeah. Yeah, I see what you're saying. Oh, that's interesting. So, yes. Okay. Nice one, Rajan. That's very good. So that gives us, okay, in order to infer the corresponding. Okay, so these are a different set of matrices then, are they? The ones that have to be, and then they follow a different rule of construction. Guessing. Yeah, so this would be one of the matrices comes out looking like this because it has this intersection. And then you can add them together and then divide by I or whatever. diagonal matrices. Yeah. Okay. Altogether, there are that many. In order to construct the generators of the SU, so these are the special unitary 5. So these are special unitary. So this must have a determinant of 1. So on. I wonder why they do that. No, divided by 1/5 or multiplied by 1/5. And in addition, there are non-diagonal generators, 24. The number of diagonal generators, that is the number of mutually commuting generators, is called the rank of a group. Thus, U5 is rank 5, whereas SU5 has only rank 4. That's interesting. Rank of the Lie group is equal to the number of its independent Casimir operators. That is the operators that commute with...
So rank is not the same as the dimension.
No, they're not mentioning dimension. Yeah.
I'm saying in general, that's what I was trying to say earlier. The rank is not the same as the dimension.
Yeah, but we didn't really bring up rank. This is the first time we're bringing up.
I was looking into that, the rank.
Oh, you were looking into it separately, not here, like.
Yeah.
Okay. Simplest and most important Casimir operator is the quadratic form, namely some a.
Casimir.
Yeah. It's equal to the number of. So they're operators that commute with all the generators. Okay.
The Casimir is connected with the charge, right?
I don't think so. Well, yes, but I think in this situation that it's referring to something completely different. But I could be wrong. Will we look it up?
Yeah.
I think this whole thing is really just a mathematical exercise to prove something, like a bit like with the. Maybe you're right. Yeah. Our Casimir element in mathematics, Casimir, also known as distinguished element of the center of the universal enveloping algebra of Lie algebra. A prototype example is the squared angular momentum operator, which is Casimir element of the three-dimensional rotation group. Or generally, Casimir elements can be used to refer to any element. All right. Okay. So you get the idea. It's a mathematical thing in order to prove something. Which is what I was thinking. So basically, it'll just be used to prove a bit like what we're doing here, like the way they're just using it to prove this is the size of this group and this is the size of that group. I think the Casimir operator is just coming in to do a similar kind of play a similar role. Okay, in order to realize that SU5 is the smallest semi-simple unitary group, incorporating all gauge groups of interactions, as the color group. Oh yeah, so we looked at this. We simply need to enumerate the operators. U1 and SU2 have rank 1, and SU3 has rank 2. So the unitary gauge group must have at least rank 4. Indeed, SU5 has rank 4 as discussed in the previous section. So we were just discussing that. To determine the explicit structure of SU5 as the unified gauge group incorporating the above 3 groups of interactions, we consider some experimental facts. One is that the color group SU3 is completely blind with respect to the weak interaction. Red, blue, and green quarks of the same flavor carry the same electric and weak charge. That implies that the groups SU and those need to commute with each other when unified within SU5. So, yeah, there's a lot of stuff there. That's quite technical. And what I'm doing over here is a lot simpler. So I'm just, a bit worried whether I'm wasting my time. On the other hand, the leptons. So the question is, can all this fancy mathematics be done out of these relations, or are they mutually exclusive? I don't know the answer to that. Okay, Rajan. Well, I think we'll call it a night there because I'm kind of sick and
Okay.
I've got a slight cold or something. So it's not making my life any easier. Let's put it that way. And so I need to go get a drink. Or
we won't have next week. So
that's right. You're away.
16th. Yeah, I'll be away. So
Great.
16th we'll see again 16th. Then 23rd I will have the history of physics 8th episode.
Great. Okay,
so we will do very similar thing, right? 16th also we'll do similar thing like today. Right?
Yeah, I think so.
Yeah,
I'm gonna see you then. Bye bye.
How was your Halloween? Good.